Thanks everybody for attending a new Bytes of Innovation webinar. It's not just a new webinar, it's actually a whole new season of webinars. After a summer break, we are now starting with a new season with some very exciting presenters, including Nina Kotler, who is the Associate Chief Medical Officer with a focus on clinical AI at Radiology Partners. And we'll have Ryan Lee, who is the Chair of Radiology at the Thomas Jefferson University Hospital, and people like Erik Ransgaard, who is the former president of the European Society of Medical Imaging Informatics. So many more exciting presenters will be lined up. We're talking to them currently. So stay tuned and make sure to attend all Bytes of Innovation webinars. So what is Bytes of Innovation? We provide a deep dive into the future of medicine. And we do this together with renowned researchers, physicians, investors, and lawyers. And we do it every other Thursday. So today is the first one of this season. And from now on, every other Thursday, we'll have a webinar. The concept is 15 minutes of presentation by the presenter, and followed by 10 minutes of Q&A, which is moderated by Aline Lutz, who is the Senior Medical Director at Segment, and by me. So to all the participants here, make sure to put your questions in the chat so that we can discuss them during the Q&A phase of this presentation. And today, I'm very proud to announce that we have Veit Sandfort amongst us. Dr. Sandfort, he received his medical degree from the Technical University of Munich in Germany. After becoming board-certified cardiologist back in Germany, he spent time at the NIH Clinical Center in Maryland in the United States as a visiting fellow and later as a staff clinician. His research focuses on cardiovascular imaging, and currently he is a radiology resident at Stanford, and that's actually where Veit and my paths really crossed. He has significant experience with big data, with machine learning and deep learning, and especially when it relates to the medical imaging and cardiovascular imaging space. So today, Veit is going to talk about new segmentation methods for medical imaging. So Veit, the floor is yours.
All right, thank you very much for the kind introduction. Yeah, I want to talk about what's new in segmentation. And I think there's some interesting things going on at the moment. So no disclosures here. I want to talk about three topics. First, I want to look at the progress or lack of progress we've seen over many years in segmentation compared to other areas of AI. Then look at transformers, use of transformers in segmentation, and then have a look at generative models such as GANs or more recently diffusion models and how they can be used for segmentation. Just a very brief look in the history, I think good to know. About 2014, something changed in segmentation. So 2013, the best segmentation methods were still based on traditional feature engineering. And you can see they were able to detect objects, but the segmentations were really not really good. And then 2014, people started using convolutional neural networks for segmentation, and we saw significant improvement, although the segmentation are still far from perfect. And then 2015, that was a really important data point. Ronneberger and his colleagues came up with the unit, and I think nearly everybody will have seen multiple of these network graphs for the unit. And at the time, that was really like an incredible advancement. So you can see here the contours. It really gets the contours right. It gets a lot of things right. And everybody who used it at the time, I think it was like magic because it just worked out of the black box so much better than you would have expected. The problem with the unit is really, the success of the unit, I think, was a little bit of a curse for the field because you have this unit that works so great and kind of innovation stalled, and everybody made like variations of the unit, which in the end weren't really better than a plain vanilla unit. You can see that here, that from 2015 to 2020, the best performing networks were just units in segmentation. Nothing really changed. At the same time, if you look at other areas of AI, for example, image generation, with GANs from 2014, you see like very generic faces, then more realistic looking faces. Then in 2018, like pristine looking, super realistic faces. And now in 2022, we have diffusion methods, which create these absolutely stunning images, and not only random images, they also, you can guide them. So this image was generated by telling the network to create an old Viking with a beard. I mean, that's like pretty significant progress in that time. The same happened in natural language processing. I mean, that makes rapid progress. For example, 2000, like in a question, that's a question answering task. And in 2017, the best networks got these questions right less than 50% of the time. And in 2022, the best networks get it right more than 80% of the time. And that's actually better than the average human. And if you see the answers of these most recent networks, you will be surprised on how good they are. So why are these other areas of AI improving so rapidly? I think it's three major points. Innovations in architecture. Of course, we now have transformer networks, the GAN methods improved, and we now have these fantastic new diffusion models. Then, of course, in the meantime, there were advances in GPU compute that is available, or maybe it's more the ability to use that compute in a more effective way. And then now we have for these other topics, we have large unlabeled or weakly labeled data sets. For example, there's this text data set, the pile, 800 gigabytes of text. For reference, the whole of Wikipedia is 20 gigabytes. And there is this huge 5 billion image text per data set that these very recent generative networks are trained on. So let's have a look at transformers. So is it really the case that, there's a concern for transformers being like super powerful machines, and maybe the CNN is not as good. And yeah, we'll see how that will turn out. Just want to briefly compare CNNs versus transformers. So on the left side, you see a CNN, and you can see that each neuron, so to say, in each layer, only sees a tiny area of the prior layer, basically the kernel size. And over multiple layers, in theory, you get a large receptive field, but in reality, that receptive field is usually much smaller than it could be. And basically, these CNNs have like an inherent bias to only focus on local features. On the other side, transformers, here on the right side, you see a transformer network. They were designed for text. So they take in a sequence of tokens, process this sequence, and output a sequence. So it's basically like a sequence to sequence network. And the difference to CNNs is that in each layer of that transformer, each neuron, so to say, can decide which input tokens it pays attention to. So it can freely decide to select any of these input tokens, and is not constrained like the CNN to a local area. For example, if you look at this sentence, the word they, so that using unsupervised training, the transformer will figure out that this word they pertains to transformers, even though these words are far away from each other. I mean, that's great, but we are looking at images. So how does it help with images? And it didn't take too long for researchers at Google to come up with a way of using transformers for images, basically by cutting an image up in small patches and then presenting these patches as basically a sequence of tokens again to the transformer. Then the transformer does its magic, and they used it initially for classification. And if there is enough data, they work really well. In medical tasks, it gets a little bit more complicated because we want usually have 3D data, or often have 3D data. And to make this more efficient, researchers at NVIDIA came up with a nice idea to make a hybrid of a transformer and a unit. So in this case, the network inputs a 3D volume, and there's an encoder that is basically like a transformer. And the decoder is basically the half of a unit. So the decoder is like a unit decoder, the encoder is a transformer, and then this network can perform segmentation. And there's different variants of this idea, and there's also purely transformer-based segmentation networks, but this one is really nicely evaluated. So that's why I'm showing this one. So they trained this network with a pre-training, unsupervised pre-training on 5,000 CTs, and then applied it to several like standard medical vision tasks, segmentation tasks. And as you can see here with the bold letters, it basically is in most categories, the unit transformer is the best performing network. You still see that the unit kind of snatches a few wins still. But overall, this is really important point that we finally, after many years, have a new method that really outperforms a unit consistently. Yeah, is this a major revolutionary change? I don't think at the moment this is not a major change. This is more an incremental change, but it is important because now we have a new method that is better than a unit. And I think there's hope that the performance of this will further increase. Why do I hope that? I think that's another feature of transformers that you saw in natural language processing, and we also saw in classification, and I think we will see it in segmentation at some point, is that these transformers are incredibly scalable. So the more data they get, the better they perform. For example, here is a recent study from Google. On this graph, you see the error rate for classification, and you see the larger you make the model, the lower the error rate. So it's scaling very far. The larger the data set you give to this model, the lower the error rate. And most importantly, the more compute you throw at this model or at this problem, the lower the error rate. And the interesting part is it's not even in this study is not flattened out, it's not bottomed out, it still might go lower. But please keep in mind that this last dot here is the result of 20,000 TPU core days computation, which is an insane amount of computation. So that's far out of reach of most research groups. But we can see on this graphs that the scaling ability is really incredible, and I think we will get more improvements from transformers in the future. All right, now let's look at generative models and segmentation. It's like, why would we need generative models? We already have terabytes of images. Why would we want like new images? But maybe it is that the task of generating imaging is a really good pre-training for segmentation. Maybe it's not a coincidence that humans who learn about anatomy usually learn it best by using paintings or drawings. They don't look at photos to learn this. So it's easier to learn from good paintings and systematic paintings. Maybe the same is true for computers. So for generative models, most will be familiar with GANs. Just going very quickly through that. Basically, you start out with a bunch of random numbers and have a generator that, based on these random numbers, generates an image. And then you have a discriminator that decides if it's a fake image or a real image. And if you have the right kind of data set, if you have a fine-tuned GAN, you will get absolutely stunning, super realistic results. But it can be finicky to get there. And then now there's this new idea. It's like such a fantastic, incredible idea that this works, is diffusion networks. Totally different approach. The idea here is, I can't go into the details to that time, but basically you take an image, you add noise successively, in more and more noise. And then you train a network, usually like a unit or like a unit transformer, to denoise at each stage of this process, each intensity of noise, to learn how to denoise that. And if you do that, then you can give this network basically random noise and let it denoise it, and it will turn out to produce beautiful generative imaging, which is absolutely incredible. So now we have these generative models, but we want now to have better segmentation. So what's the plan? So, I mean, we know some parts of the plan. We need or we have a large amount of unlabeled data. If you don't have it, I guess Segment can certainly help you. With that, you can train a generative model on this. And then, I mean, you need some segmentations. So hopefully a low number of manual segmentations to kind of make it clear what is what. And then you need to do something and hopefully get fantastic segmentation. So the question comes down to what is that do something? And this do something, for example, could be this. So this is a study from NVIDIA. They are really very good at GANs. They used their style GAN and slightly modified it to not only generate like photographic like images, but at the same time produce a segmentation mask. So then there will be like a discriminator that looks, is it a real or fake image? And a discriminator that looks, is this a true or fake segmentation mask? But that alone wouldn't work on its own, because there has to be some connection between the mask and the image. So for a few examples, so they did the segmentation, as I mentioned, for a low number of samples. And for if you have the segmentations, then there will be an additional segmentation loss on this generated map here. But for most cases, it will just use the discriminator for training. And here is the result of that. I'm not sure how good the video transmission is here, but I'm looking at numerous really realistic looking images and pretty good looking segmentation maps here. So it's pretty fantastic, basically. So it's amazing. And they also use this for medical images. So they trained the same thing for chest x-rays and used this for segmentation. And you can see it's equally good as all the CNN-based methods. It gets more interesting if you look at slightly out of distribution data, like different hospital, different data set. And that is a little bit like the dirty secret of deep learning. All these methods completely collapse, with these out of distribution data. For example, this is a perfectly fine looking chest x-ray, and every CNN comes up with that idea that there's a third lung here, which is of course totally absurd. But interestingly, the GAN-based method is really more robust and gets all these cases right, basically. So I think that robustness is like a huge thing. So that's really promising. That's just one little problem with that, because if you want that segmentation mask, you basically need to you need to make the GAN create exactly the image that you want the segmentation from. That's called GAN inversion. Basically, you have to find this secret random numbers that generate exactly the image you want, and then you get the segmentation mask for free. So how can you do that? Basically, if you want this specific image, you can start out with the most average looking chest CT, and then during an optimization process, try to make it look like this one. So like so. So that looks pretty close. So yeah, problem is maybe solved. The thing is, it doesn't always work. For example, here's the real image that has these bright spots in the right atrium, which are pacemaker leads. And if you ask the system to make the GAN image, matching this image, it comes up with this fake image, and these leads are just disappeared. So I think this is a really, really serious problem for medical applications, and I don't see a fix, an easy fix for that to really get to that specific image that you're interested. So that's a major shortcomings of GANs. Now let's look at the diffusion models. As I mentioned, the basis is to add noise over numerous stages and then train the denoising. This is a study from Yandex Research, a data science company. And the denoising process, basically at each level, you use a unit-like type network to denoise this image. And during the process of learning, the presumption is that it will learn some characteristics of the image, because if you want to denoise this specific pixel, it might be helpful to know, hey, this is a face and this is a nose and this is supposed to look like this. So during the denoising, you can use some background knowledge, and this knowledge is somewhere in this network after training. So they try to extract that knowledge, basically giving the specifically noised image, having it denoised, and kind of harvesting these activation maps out of the unit. And then you get this very large feature vector for each pixel, and you can use a classifier on that and get segmentations. And just how useful are these feature maps? Here's just an unsupervised clustering of these features. And you see already there's some meaningful things in there. There's like structures like hair or facial features somehow already in these feature maps. So they might be helpful. And if you train them in a supervised manner on all these different data sets, you get really, really good looking segmentations out of this. Here on this, the rightmost column is the new method. And keep in mind, these images were only trained on 20 to 50 sample segmentations, which is a really low number. So I think this is very promising to be very label efficient, and that's what we want basically. So I think this looks really promising. So in conclusion, after many years of stagnation in segmentation applications, there's really now suddenly very rapid progress. And the interesting thing is, people I talk in the medical world who are like up to date usually, they are not aware of this sudden progress that's happening. It's kind of surprising. Also, transformer networks have already surpassed CNNs in segmentation tasks. And as I mentioned, there's much more to come because these models that are currently used are relatively small, and there's potential to really scale them up to much bigger sizes, model and dataset sizes. The GANs look amazing for segmentation, but as mentioned, they have really, really big issues. I don't see this, how to fix these issues. For medical imaging, for other applications, I think it might be still useful. And then the diffusion networks are making just incredible progress, and I'm absolutely sure that this will be there will be much more to come from this direction, either this or a combination of transformers and diffusion networks, I would guess. All right, that's thank you for your attention. That concludes the talk portion. Happy to take any questions.
Thank you, Veit. That was super interesting. Thank you for sharing all this knowledge with us. We do already have some questions in the chat, but I would like to start with a question which is more basic. So for people who are starting in the field, how is segmentation useful for radiology images? And so how, and I mean, why do we use segmentation? And the same for synthetic images.
Yeah, I skipped that part. I had that in the talk, but I skipped it out for time reasons. But basically, you could argue a lot of tasks in medical imaging are classification. Maybe like, is there a bone fracture? Is there a brain bleed? And so on. Is there a pneumonia? So most of these competitions are based on classification actually, but always the next question is, how big is that brain bleed? How large is the area involved with pneumonia? And you immediately come into, or where is the fracture? You immediately come into the realm of segmentation. The other, I think the basic need for segmentation comes from the quantification, as you can see here. If you want to see on an MRI, how large are the cardiac chambers? You need the segmentation. I mean, also for heart flow, for example, a company that is very successful for determining stenosis in the cardiac vessels, that is the core of this method, is actually a very precise segmentation. And this is really a method that's highly reimbursed by payers because it's a high value. It's a high value method. You can do the CT, you do the analysis, and the patient doesn't need a cath. It's very, helpful for the medical system, and it gets very well reimbursed for that. So it's a high value method. Also here in lung, in lung tasks, finding diseased lung, that are methods that are very close to commercialization. So I think in many fields, tumor size, I mean, there's just so many questions that need some kind of segmentation. So I would say that's there are many important tasks, if that answers your question.
Yeah, I'm sure it makes sense. So at Segmentation, we provide diverse data sets, and not only diverse coming from different hospitals and covering different populations, but also in terms of disease severities, number of lesions, and lesion sizes as well. So yeah, it makes sense. So Jay is asking, so he says, transformers are developed for text. How is the performance with medical images?
Yeah, totally right. They are developed for text, and there's two ways basically of doing this. One is really cutting the image up into slices, into small patches, like maybe 16 by 16 or even 8 by 8, and then making a sequence out of these patches and treating each patch like a token. So that surprisingly just works. You have to train it a lot to get it to work, and you have to do some. You can also do some additional changes, because in a transformer usually there's like a positional encoding, like this is token 1, this is token 2, this is token 3, and so on. And for this task, you can add like a 2D positional encoding, saying this is square 1/1. This is square, XY coordinates for each square, basically. So these are the ways. And then there's other methods where you can use specific types of autoencoders, like VQ, quantive autoencoders that can convert an image basically to a token, to discrete tokens. So you can use all these methods, and it works really well.
Awesome, that's great. Veit, I want to thank you as well for a great presentation and a good discussion here. We have more questions. I actually have a bunch of other questions, but we don't really have that much time. So I'll ask this question that Domenico is asking in the chat is, there are still some substantial challenges like limited compute with transformers, but what do you think will be the role for transformers for medical imaging segmentation purposes?
Yeah, I think the compute is a problem, but there is hope. These initial transformers were super resource intensive, and I think people came up with multiple tricks to make them more resource efficient. So I think hopefully over the next year or two there will be further improvements to make these transformers more usable with normal compute amounts. And then I think the goal is to train to use a very large data set and to train a very large transformer, which will take maybe weeks to train, and then publish that for other people to use. So other people can take this pre-trained transformer like a language model. It's like GPT-3. Nobody trains GPT-3 at home, but you can use it basically. Well, not really, but you can use other huge pre-trained networks, language networks which are open. So that's the idea, to make a pre-trained network, and people could use it and fine-tune it on their specific problem, like BERT, for example, the BERT transformer, which you can train on you can fine-tune on your home computer.
Yeah, that makes sense. Actually, at SegMed, as you know, we have access to a lot of data, so this is definitely something we should talk about. Maybe we could do a cool research project around this.
I think the access to the data is a big plus here. Yeah, definitely.
Yeah, awesome. Okay, well, thanks, Veit, for an amazing presentation. Super, very informative. Lots of high-end new information. So thanks for that. And I also would like to thank all the participants for joining this webinar today. In 2 weeks, October 6th, we'll have Ryan Lee, who is the chair of radiology at the Thomas Jefferson University Hospital. So all make sure to join again in 2 weeks. And thanks again, Veit, for a great presentation.
My pleasure. Thank you.
Thanks, everybody.